So we go back to our data. Again, same set of data. This time we're interested in the improvement, but in the paired observations test, we actually input this data, and then SPSS, Megastat actually calculates this for us. We'll never see this column calculated by Megastat, but it will nevertheless calculate this as a part of its routine. Okay? So once again, we're going to work with Megastat. So we go to add-ins, and then we drag over to Megastat. We drag down to hypothesis tests. And in this instance here, since we're going to compare two related groups, I should explain that momentarily. Since we're going to work with two related groups, we run the paired observations test. And for group 1, we will put in the students' exam scores for exam number 2. And for group number 2, we put in the exam scores for group number 1. And hypothesized difference, we'll hypothesize 0 difference. And we'll set it up as a two-tail alternative test here. And we'll do the 95% confidence interval, and we ask for the lower and upper bounds of the confidence interval. Now, before I click on OK, one thing I should explain is the reason why it's legitimate for me to do paired observations here is I can calculate or identify student number 1's exam score on the first exam and the same student's score on the second exam. I can identify and match that for student number 4, on the first exam he or she scored 92, and on the second exam that same student scored 91. I know that on the first exam student number 8 scored 90, and on the second exam that same student scored 80. So the reason why we use the term paired comparisons or paired observations is because between the two groups we can match each. Not only could we compare two means, 78.7 to 80, not only can we compare two group means, but on an individual basis we can match each element from our sample. We can match observation number 1 with observation number 2. Okay? So that's what makes it related groups instead of independent groups. So now we just click on OK. And let me see if I can... Okay, the first thing I said earlier was that paired comparisons and the one group difference of means test are computationally identical. So when I ran the when I ran the one group difference of means test, I got a t-value of 0.368 and a p-value of 0.7213. Notice for my paired comparisons test, I got exactly the same observed t and exactly the same observed p-value. So that confirms that computationally the paired observations and the one group difference of means test are the same. And the same thing for the confidence intervals and the margins of error. You'll notice that they are identical. They may be off, to the 1/1000ths or 1/10,000ths just from a rounding error, but our margin of error, as well as our lower bound and our upper bound of our 95% confidence interval, those are all identical. And the reason why this bottom portion of your output from the paired comparisons test is identical to your output from the one sample difference of means test is because those two tests are computationally identical. So it does not matter, computationally, it does not matter when you have a set of data whether you would run it through the one group difference of means test only using the improvement column or the paired comparisons test where the Megastat problem asks you to specify one of the groups as exam number 1 and one of the groups as exam number 2. Regardless, you get exactly the same statistical output. Had you ignored the fact that we could match our observations on a student by student basis. Had you ignore that and only run a two-group difference of means test, you see from the megastat output that the results are very similar, although slightly different from what we got for the one group difference of means in the paired comparisons. I think you need to study that memo that I distributed to you covering this same material, just to make sure that you really understand conceptually the empirical point that I make in this mini lecture. Thanks.